Hello, everyone, and welcome to our third seminar of the series of the Latin American webinars in physics. My name is Jorge Diaz from the Karlsruhe Institute of Technology in Germany, and I will be your host today. Our speaker is Dr. Isabel Pedraza from Benemérita, Universidad Autónoma de Puebla in Mexico, who will talk about the Large Hadron Collider and some results from the CMS experiment. She received her PhD from Benemérita Universidad Autónoma de Puebla, working at CERN. After a postdoctoral position at the University of Wisconsin, working for the ATLAS experiment, she moved back to her alma mater, where she is currently a professor, now working for the CMS experiment. Isabel's talk today is titled "The Status of the LHC and Results from CMS." And we're really happy to have her as our speaker today. Let me remind you that you can post questions just so you can join the discussion. You can write your questions on the comments or using this Google Plus Q&A system. And you can also use Twitter with the hashtag LAWOP. So I will not hand you over Isabel.
Hi, hello everyone. Sorry, thank you very much, Jorge, for the nice introduction. So as he mentioned, I will talk about CMS and the later results that were almost presented in Morion, all of them, and the current status of the LHC and the plans for this second round that we are starting. So I will start sharing my slides. I will start with what we already know since 2012. The LHC, the experiments ATLAS and CMS of the LHC discovered a particle in 2012. And after that, after few more analysis to see whether this particle that was discovered in 2012 was the Higgs particle, and at the end of 2012, at the beginning of 2013, the particle looked like the Higgs particle. So decaying into fermions, decaying into the normal ratio as is predicted by the mechanism of Francois and Higgs, and the Nobel Prize was given in 2013 to
Isabel,
Francois.
it seems we're having a problem with the presentation. We're not seeing the slides.
Really?
Yeah, can you just check the share screen just for a second?
Okay.
For the interrupted, but we're not seeing the slides.
Sorry. Now you do.
Yeah, now it's working.
Okay, I'm really sorry then.
No, that's fine. You can just go ahead.
So it's just the first slide. So as I mentioned, LHC round 1 had a great success due to the discovery of the new particle and the confirmation of the Higgs particle in 2013, and the Nobel Prize given to Francois and Engler. So I will give you a fast introduction about what is the LHC. The LHC is a hadron collider of 27 kilometers of circumference, and it is underground between 100 meters in most of the cases for the experiments, and the collisions that were happening in this collider during 2010 and 2012 were between 70 tera-electron volts and 8 tera-electron volts. In total, we have around 400 million of collisions per second, reduced by the trigger selection. There is around 1% of the events that happen in the collisions, and it reduces to 500 events per second. It is in between France and Geneva, and it's close to its. The main offices are in Switzerland. The LHC performance in round 1 was very, very good. and the first part of the data taking gave us around 6 inverse femtobarn of data, and in 2012 at 8 tera-electron volts we collected 23 inverse femtobarns of data. That gave us around 250 Higgs per event, 250 Higgs events per hour, and the instantaneous luminosity was 7.7 to 10 to 33. And we remember that the nominal peak luminosity for the LHC was 10 to the 34. The main challenge during the first run was the many the number of pileup of the number of vertices that we had in every bunch crossing. In this example, in this slide, I present an event with 78 reconstructed collision vertices and 1 bunch crossing. In average, our number of vertices in the collisions was around 20, 21, and from it we had to select the good vertex and the good collision. Though all the experiments, SUP detectors in the CMS, and mainly the inner detector, was designed to be able to reconstruct this amount of collisions, and it was of course a challenge for the trigger, but we managed to do it for the first run of the LHC. A real picture of the CMS, where 2,680 physicists are working, where 891 of them are students, PhD students mainly. We are 182 institutes from 42 countries. The CMS height is 25 meters, and it is 15 meters diameter. Here are a slice of the CMS just to get familiar with how we do the detection of the particles. In the center of the left part of this image, we have the tracker where all the charged particles leaves their signal, and then we can reconstruct the trace or the path where they went. And then after that we have the electromagnetic calorimeter where all the electromagnetic interacting particles are stopped and we collect their energy. Then we have the hadronic calorimeter where all the proton neutrons are stopped and we collect their energy. And we have a muon system. The particles that go deep into the experiment are the muons. So we have all this muon system in the outer part of the detector. And the neutrino, it's not that we cannot detect neutrino, of course. So we call the neutrino missing energy. So every time that I mentioned missing energy, it meant that it's something that we could not detect, and mostly is due to the neutrino. We have in CMS we have 2 magnetic fields, one in the inner part at 4 Tesla, and in the outer part where the muons are, it is 2 Tesla. That's why you see the muon track, the blue one, is deflected into different directions. The CMS physics analysis are currently, or in the first run, the analysis that we did were about a standard model physics. Of course, we had to get the results from the previous experiments and corroborate the measurements that already existed. We have forward and small x QCD. We have heavy ions physics, B physics, Exotica, top physics, supersymmetry, and beyond 2 generations physics. Of course, our main subject during the first run was the Higgs that has been searched for more than 40 years, and it's what I'm going to present today mainly. So this, the production of the Higgs in the CMS can be done by 4 processes. One is a gluon fusion, where in a mass of 125 giga-electron volts is the mass that we found the Higgs. The production due to the gluon fusion is 86%. We have also production of vector boson fusion. It is around 7% of the production. The associated production with the W03 is about 6%, and the associated production with top is 1%. At 8 teraelectron. That means that in the second part of the run, where we were colliding at 8 teraelectron, we had around 400,000 Higgs bosons produced in the CMS. How do we distinguish between this Higgs production? Because after that you will see that in all the papers we are dividing the different processes. So how do we distinguish between different processes? In the gluon fusion, there are no jets, and in the final state there are no jets associated. So when you have 0 jets, it means that the Higgs was produced. We assume that the Higgs was produced by the gluon fusion. In case you have 2 forward bosons, 2 forward jets, we assume that the production is done through vector boson fusion. In the case of you have an associated production, of course you will have the Higgs plus a W or a Z decay. And in the case of associated production with the top, we assume that we will find the ditop and the Higgs. The decay after having the Higgs produced, the decay can be into direct coupling with the mass particles like WWZZ, tau tau BB, or through the loop of tops, giving us gamma gamma or gluon gluon. In the case, we are very lucky that the Higgs like to be in the 125. You can see from the plot that it's a very favorite mass value, because we have all different decays into in this mass value. If we have a Higgs at 400, for example, we wouldn't have the gamma gamma decay available, or the tau tau decay. So we are very lucky. And in the case of having produced 400,000 Higgs at 125, if we have a branching ratio for the gamma gamma, for example, of 0.002, we have 800 Higgs to be found via gamma gamma in the second part of the run at 8 teraelectron volts. It's what we were searching. And here is one example of one of the decays, one of the event displays of Higgs candidate going to CZ, to 2 muons and 2 electrons. So you can see from the picture that all the muons touch the muon detectors, the red ones, and the electrons are have a signal in the tracker plus the position in the calorimeter, the green part. So this is a candidate with a mass of 244 gigaelectron volts. Of course, is not associated with the Higgs peak, but it was one of the first events of this class. In this case, the analysis done for the Higgs going to ZZ gave us a signal, and the strength of the signal that we call signal strength is the cross-section that we observed over the standard model cross-section, and we expect this value to be close to 1, and in this case for this channel is 0.92. As you expect from what I mentioned, the main signature here is when you find 4 leptons. It can be 4 electrons, 4 muons, or 2 of each one, as in the event display. The advantage, this is called the golden channel because it's the cleanest one. The advantage is that you have more signal than background in the signal region. You can see from the plot in the left, the peak, the red peak corresponding to the signal. It's in that region, the background is very low compared to the signal. It can be fully reconstructed. We don't have any misenergy in the event. You can do measurements of spin and parity. And the bad things about this channel, it's that we have a small signal. and it's a challenge to keep the high lepton efficiency. The lepton efficiencies are above 98% efficiency for both for electron and for muons, being better for electrons. And the dominant background is the ZZ production and all the fake leptons that are coming from the jets. For this channel by itself, we have already a discovery using the complete set of data at 7 electron volts and 8 electron volts. And we use, apart from the mass, we use a variable distributed, a discriminated variable that uses all the angular distribution of the particles, of the final particles, to do this, to calculate this sigma or p-value. In the case of Higgs gamma-gamma, what we search is, of course, two gamma-gamma particles, where the gamma-gamma particles is just at the position in the electromagnetic calorimeter without any trace associated. And in this case, we have two forward jets, so we know there is a vector boson fusion production in the event. This is the event where the signal was seen for the first time. It was the one that had more visibility at the beginning. The advantage of this one is that you have two isolated leptons, and the spectrum of the PT is the efficiency is very high, as the same as the Higgs to CZ or the Higgs to 4 leptons. You have a fully reconstructed final state. You can reconstruct the mass. The resolution for the mass is really efficient. It's 1–2% of efficiency in the mass reconstruction, and we have a large signal in comparison with the background. The challenges are collision vertex assignment. Since we don't have a trace associated with the gamma-gamma, the reconstruction of the vertex is it's one of the main challenges. And since we model the background, we do a fit to the background, it was also a challenge to match with the data and all the data-driven methods to reconstruct the function that gave us the modeling of the background. This one can be, this analysis can be split in many different categories depending on the kind of photon. We have different categories for the photon reconstruction, and it gave us, when we split in different categories, it gave us a large sensitivity for different categories, and that helps us a lot in the calculation of the sigma of the discovery. So in the plot, what you are seeing is the invariant mass reconstructed from the gamma-gamma, from the two gamma-gamma founds, and all the different categories are some in this plot. In the lower part, you see the data with the subtraction of the background. The discovery that the sigma value that we get just from this analysis is more than 5 sigma. So it means that we have a discovery with this channel by itself. I remind you that at the beginning we had 3 sigma, and it has been growing from a time in the time as the data has been taken in this channel. Another channel that we looked at was Higgs to the WW. Each one of the W's decay into lepton neutrino. Here we have missing energy coming from the 2 neutrinos. In this 7 display, you have a Higgs going into WW, and each one of the W's going into electrons. You see the position in the electromagnetic calorimeter, and also the trace associated to it, and the direction of the missing energy that is given by the compensation of the energy that you don't find in the transverse plane And in this analysis, the main challenge is the reconstruction of the missing energy. As I mentioned, it's associated with the neutrinos, but we don't know the direction of the neutrinos. We know the direction of the total missing energy, but not the specific. So what we do is we reconstruct the transverse mass instead of the invariant mass. The advantages of this channel is that we have an acceptable ratio between the signal and the background, around 0.2. The challenge, besides the reconstruction of the missing energy, it's that the resolution for the missing energy it's 20%. Compare that to the resolution that we had for gamma gamma, for example, that was 1%. So here the resolution is much more wider when you do the analysis. So that it's that's why it's less. This channel is less competitive, we can say, with the gamma gamma or the 4 leptons. The main backgrounds for this channel, in the previous analysis, we had just in the case of 4 leptons, we had just the production of the 2 Z's. In the case of gamma gamma, we had the profile of the regular gamma gamma production. In this case, we have 5 backgrounds, and each one of them require different considerations for the modeling. We use Monte Carlo for some of them and data-driven for some other, and all this requires more validation and more work than for the other channels. In the case of the WW, we see a significance of 4.3 instead of 5.8 from the expected. Of course, because as I mentioned, the difficulties or the challenges that we have in the analysis, and it's not yet a discovery by itself, but going into the same direction and the same mass value for the same mass value for the other channels. In the combination, it gives pushes the significance, the combined significance up. In the case of tau tau, this was one of the important channels after the discovery, because we wanted to know if there was a direct decay on leptons, on fermions, and we know that if we were seeing the Higgs to gamma gamma in the Higgs to gamma gamma, it was through a loop of tops. Nevertheless, we needed to see the direct decay, and this analysis was one of the most important analyses after the discovery and after seeing the other decays. In this event display, I show you a Higgs going into tau tau. One of the taus decay hadronically, and the other tau decays electronically. That means in this case, it decays into a muon and into a neutrino. That gives us the missing energy. In this case, and we have in the event display, we have 2 jets. I remind you that when you have 2 jets, it's a vector boson fusion production. For this analysis, the main but we have big challenges for this one, because the ratio between the signal and the background is very small, and we have large uncertainties for this one. Starting from the reconstruction of the mass, since we have missing energy, we cannot reconstruct completely the mass. So that is one of the problems. Then the reconstruction of the mass of a Z, the main background is a Z to tau tau, but it has the same challenges to get this profile. It has the same challenges as a simple reconstruction of tau that has low efficiency. So to do that, we did a procedure using the Z to mu mu signal and mixing this information from the data with the decay with the Monte Carlo of the tau together to get a sample of the background that can modulate as we see the data as good as we can the data. So the uncertainties of doing that was really large in comparison with the other analysis where the main background is coming directly from the Monte Carlo or data driven. But this one was a mix, so the uncertainties multiply, and that's why it was really a challenge to do this reconstruction. The main background, as I mentioned, was C2 tau tau and the QCD. In this channel, we have a signal strength of the ratio between what we see, the production that we see, and the production predicted by the standard model is 0.78 in comparison with the standard model, and the uncertainty is 0.27. For this channel, we have an observed significance of 3.2. It's already an evidence that pushes up the combination of the significance for all. And since we saw the decay on this channel was very important to see, it was presented in Morion in 2013, and it was one of the key things to confirm that we were talking about the Higgs particle and not another boson. Another important analysis that is also difficult is the Higgs to BB. In this event display, I have a Higgs decaying into two Bs, and you have the two jets corresponding to the vector boson fusion production. The reconstruction of the Bs is also something difficult because the final state is seen as two jets with a small displacement in the main vertex. Here, the advantages are that the branching ratio is very large. The challenge is that the ratio between signal and background is very poor, and to distinguish between the background and the signal is hard. Also, the efficiency of reconstructing a V is very low compared to a lepton, for example. The mass resolution for this channel is around 10%. And one of the key points, of course, is the B tagging to recognize that the jet is coming from a B and not from other jet production. The backgrounds, it's also a combination of backgrounds. We have top, diboson, and QZD, together with the vector boson production associated with jets. For this channel, we have an observed significance of 2.1, and this significance is not even an evidence. Nevertheless, it gives us a push into the combination, and also it's an important channel for what I was mentioning before, the same as the tau tau. In total, the signal strength for all the channels, these are the legacy combination that CMS has done, and it's already submitted for publication, and it was presented in Morion a few days ago. We have the different analyses, the ones that I presented: Higgs to gamma gamma, Higgs to CZ, Higgs to WW, Higgs to tau tau, Higgs to BB, with the different category of the production. Untag means the gluon-gluon fusion, and vector boson fusion, you have associated production and top associated production. In the case of gamma gamma, we have a strength of 1.12. CZ, it's closer to 1, and in general, all of them are close to the line, to the green line vertical line, sorry, that it's corresponding what we expect from the standard model, and the combination of all these values is 1. I mentioned that the last value that we had was 0.9, and now with all the new analysis and the new and all putting together all the data and all the channels, we are getting very close to the standard model, and it's 1 plus the different values for the uncertainties, giving us a 0.14 in total uncertainty. The signal strength was also tested in the different for the different production modes for the vector boson fusion and also for the associated in the left part of the vertical axis of the plot, and in the horizontal you have the gluon and the top production, and the contours are correspond to 68% confidence level regions. So what we expect from the standard model is the yellow point surrounded by the red, and all the other values that we see from data are very close to it. We can see that all of them are consistent with what we expect from the standard model, at least at 68% confidence level. This is also coming from the latest combination, the legacy combination. We also tested the spin and the parity of this particle. The measurements were done where we have enough signal to distinguish between them, and the measurements were done with the Higgs to 4 leptons, Higgs to WW, and Higgs to gamma gamma. You can see in the plots that in the left one, the two hypotheses of having a spin 1 and a spin 0 in both with positive parity. Those are Monte Carlo experiments or pseudo experiments, and the red arrow corresponds to what we observe on data. So we can see that for the between the spin 1 and the spin 0, the data prefers to stay in the 0 spin region. And if we compare the 0 with the spin with positive parity and negative parity in the left plot, in the right plot, the data also likes to stay in the 0 plus. So the spin 0 and positive parity is strongly favored in this. The data is strongly favored this value for the spin and parity. In this legacy paper also, the precise determination of the mass was studied. We did that with the Higgs to ZZ channel and the Higgs to gamma gamma, and the value that we got is 125.02 with different systematics. And as you can see from the different values in the tables in the right, in the case of ZZ, we had 125.6 gigaelectronvolts, and in the case of gamma gamma, the mass that we were getting was 125. So it's very consistent with the value. The combination is 125.3, consistent with what we were seeing in the different channels by themselves. It gives us a precision of 0.3% of the measurement of the mass for the Higgs. We also test the couplings. This is the latest combination that we get for the test couplings. In the vertical axis, we have the couplings to the fermions. Here we define the coupling test as the ratio of the coupling that we see in the experiment and over the ratio that is predicted for the standard model. So we expect that this ratio is 1, is close to 1, is what we expect. And in the case, the same for the coupling to the vector, to the vectors, and in the horizontal axis, you can see the different channels distinguished by the colors. Of course, we have values for positive and negative region. The only one that makes sense is the positive. And you have the different decay channels, Higgs to BB, Higgs to tau tau, gamma gamma, WW and Z. See, with the different colors in the contours. The combination is given by the gray area, and it's the error contour includes the value expected by the standard model, giving us this as a consistent result with the standard model for the test of the standard model couplings, for the couplings for the fermions and vector. It is predicted by some beyond standard models. It's predicted that we can see deviation in the loop production for the Higgs to gamma gamma and gluon-gluon fusion. We can see this testing the coupling to the gluon and to the gamma. And here we present the results that we see testing this coupling, or looking at this relationship. We expect from the standard model, as I mentioned, to be this coupling 1. The observed is around 1.2 in the coupling for the gamma, and 0.9 for the coupling of the gluon. The contour at 68% confidence level includes the contour includes the value of the standard model, so it's consistent. The result is consistent with the standard model. We don't see deviation in the induced loop for the diagrams. The test continuing with the test for the standard model couplings, it is predicted also for models beyond the standard model that we can see asymmetries between the up and down type and lepton quark couplings. So we tested these couplings, and we got that the coupling for the up and down lies between 0.74 and 1.95 with 95% confidence level, and the couplings for quark lepton, the ratio between these two couplings lies between 0.57 and 2.05 at 95% confidence level, while we expect the value to be at 1. From what we see from the standard model, what we expect from the standard model, and we can conclude that well, they look consistent within this range of the values. The summary of the coupling test that we did, that is presented in the legacy paper, it's in the left. You see all the couplings, or the ratio of the couplings. The first value is the ratio of the coupling of the W and Z, 0.92. The coupling for the vectors is 1. Coupling for the fermions, 0.87. The ratio between the couplings of the up and down is 0.99. And the coupling for the gluon, 0.89. And the coupling for the gamma is 1.14. What we see from the beyond standard model ratio is far away from the, of course, far away from the standard model, and we see something less than 0.14 from the data. So everything is consistent with the standard model for the test couplings. We did the same for the couplings in relationship with the mass of the particles in the right plot, and from it you can see that at 95% confidence level everything fits into the line that is expected from the standard model. Some models predict that in case of in case of the Higgs being not the only one or existing another Higgs, instead of having one line, you may have 3 lines of this kind. It is we are consistent with the Standard Model, but there is a space there to have something else coming from another model. In total, the summary for the Higgs analysis in the first run that were done with 5 inverse femtobarn of data at 7 tera-electron volts and 5 inverse and 20 inverse femtobarn of data at 8 tera-electron volts have been presented and published already, except for the legacy paper that is coming. All of them are consistent with the Standard Model and report mass around 125 giga-electron volts. This is what corresponds to the Higgs results, the later results for the Higgs. But CMS is doing more analysis than that. As I mentioned before, we are doing standard model, of course, to confirm what we have seen already, and also to search for any deviation from it to see if there is a place for new physics. We are doing supersymmetry. We are doing Exotica. We are doing top physics. In total, this is the results, the summary of the results that we have for the Standard Model. At the end, we are already including the measurements that do we for the Higgs. So we do precision measurements for WZ production, top production, and everything so far has been consistent with the Standard Model. We do also measurements on Exotica, everything, all the models that predict something beyond Standard Model and is not supersymmetry, including dark matter, heavy gauge bosons, extra dimension compositeness, long-lived particles. All this in these plots, we in these histograms, each one of the predicted particle is excluded up to the mass that is mentioned in the vertical lines. For example, if we pick up the W prime in the area of the heavy gauge bosons, we have an exclusion for this one. There is no W prime. We haven't seen any W prime up to 3.2 tera-electron volts at 95% confidence level. So we are doing, in parallel to the Higgs physics, we have a bunch of analysis for Exotica and plenty of results that you can find in the public results for the CMS. In case of supersymmetry, we have a separated set of a group of people doing, well, many groups of people doing many different things, and you can also find the results in the public page of the page for the public results of the CMS. Well, to finish the analysis, that is what corresponds to what I wanted to mention to the analysis. We start with LHC schedule to end more or less how it looks. The LHC calendar is expected to work to be all the way to 2035 is what we expect to have. Now we are in 2015. In the first half, in the second half, we are expecting all the green is physics. The red are the long shootdowns that we expect during this period. And as you see, the second run that we are expecting and starting in these days is going to finish in 2018. And after that, we are improving energy and luminosity for all the other program. In the specific case of this year, we are starting during March. The calendar is seen by weeks, and in the Monday row you can see the day. So, for example, today we are on in the last column of the of the first set of days, 23, March 23, and we were expecting beam this week, already a beam surrounding the LHC, but we got a little delay, so this week we will not have the beam, unfortunately. But it's foreseen very soon for next week. During this period, below this table, I mentioned that CMS has been working with all the detectors and everything synchronized, running cosmic run at 0 Teslas and cosmic run at 4 Teslas. We are already prepared to get the beam. CMS is ready to get the beam. The first beam, as I mentioned, is expected next week, and we will start the beam up to May 11. Then we will have a special rounds for physics, and we will increase. We will start changing the separation in the bunches to change from 15 nanoseconds to 25 nanoseconds in the middle of June, more or less. This is the second part of the schedule. So you have around July 6, we will start trying to get 25 nanoseconds operation for the LHC. The LHC goals for 2015, of course, is to get the energy at 6.5 teraelectron volts. You can see that all the way to March, we were able to get the energy around 3 teraelectron volts per beam. This has been going, this test and this increasing the energy has been going for 6 months. As you know, we were changing all the connections in the LHC. And we are now, it was reported, Morion, that we are now ready to go all the way to 6.5, depending on these energy tests that are done, that will be finished. Of course, we will know for sure next week. And the other goal of LHC is changing the bunch spacing from 50 nanoseconds that we have now to 25 nanoseconds. So we decrease the pileup, the amount of pileup that we are expecting. Since we are increasing luminosity, we are expecting at 50 nanoseconds to have much more pileup than we had for the first run, and there is a challenge for all our detectors. So for this one, decreasing the separation of the bunches, you decrease the amount of proton in each one of the bunches, so the pileup is decreased, and you get more safe. The trigger and the reconstruction gets easier than going into the 50 nanoseconds, where you have more pileup. To finalize, the prospects of run 2, of course, is continue with the precision measurements of the Higgs. The gluon fusion cross-section increases by 2.3 from 8 electron volts to 13. In the case of production with the Higgs to top, the cross-section increases by 4. The background increases, but we have more or less already all the analysis set. We are expecting up to 100 inverse femtobarn for the whole second run. At the end of the 2018, we expect more or less 100 inverse femtobarn. I remind you that we got results with 20 inverse femtobarn, and the most important is that all the new physics that is coming, it's going to be seen at the very beginning, because we are increasing a lot the cross-section of many of the exotic particles. The SUSY also will be, if hopefully we can see SUSY at the beginning. And it's more or less what I wanted to tell you on the LHC prospects for this second run. And for me, it's all.
So thank you, Isabel, for such a nice presentation. We will now pass to different participants, because there are several several questions now. So, but let me remember, don't forget that you can also ask questions to Isabel using the Q&A system in the webinar page. And you can also use Twitter, just in case. You can also use this hashtag LAWOP. So let's see who's going with that. We have a question from, a few questions from Valencia. So let me pass it to you.
Okay, I have one question. First of all, thanks for giving this webinar. My question is, what do you mean with this, for this CMS physics analysis? What does it mean that beyond 2 generations? In the sense that the first generation is like extra or it's apart, or if you can comment about
that. Beyond, I'm not that familiar with the analysis with beyond 2 generations. It's analysis that goes, it's inspired by Exotica, by the idea of Exotica, and it comes from for new physics, but I'm not, I'm sorry, I'm not familiar with that section of the analysis. I know that it's inspired by the Exotica, and it got divided, but I don't remember. I'm sorry.
So we had more questions from Valencia.
Okay, yes, we have more. I mean, the ones that people wrote the name, they are going to ask now.
Yeah, I'm curious about one thing. So you have presented some results of Higgs physics, and they are all perfectly compatible with the standard model, but I was wondering about Higgs to tau mu, since CMS has also observed an excess. I think it's at the level of 2.4 or 2.5 sigma. Can you comment on that?
Yes, of course. As you may know, when you see something below 3 sigma is not yet an evidence. Nevertheless, and tau is the tau reconstruction is something very hard, because also you have the missing energy involved, and it's what we are seeing, right? I cannot say that the measurements that the standard model that we are doing are wrong. It's just that we see that in the Higgs we respect everything that is close to the standard model, and in the tau mu channel we are seeing this deviation that we cannot yet say that it's an evidence or something else.
Okay, we have now a question from Peru. I will pass it to you right now. You can go ahead, guys.
Sorry, we had issues with the microphone again. I was wondering if you could give details about the low-level triggers for the next run, since we're going to have a larger pilot now. How is CMS going to adjust to that?
Well, of course, it has to. We implemented a new technology for the trigger, a new algorithms, and I don't have the menu for the lower trigger right now. It's not public yet. But of course, we are increasing the energy in many of the first level, the L1 trigger for many of the objects. It's going to get many of them are going to get prescale, and some others we are expecting a high level. I are simply just cutting up. Instead of having an electron 25, we will have electron 30, respecting, of course, the safe analysis to have the peak of the W, the peak of the Z, that are the ones that we can confirm right now. Everything that is a standard model, of course.
Thank you.
So we also have we've got a question from Jose Zurita. He said the TTH central values are rather large, but also with large uncertainties. Is this limited by systematics or statistics?
It's systematics mainly. It's also, I mean, if we don't have a lot of statistics, we also have large systematics. So it's going in both directions. We don't have a precise measurement because we cannot reduce systematics, and that is due to statistics.
Okay, we have here another question by Federico. He asks, will the present delay affect the start of the physics run?
Oh, no. No, I mean, it's just 1 week, and there is no that big delay so far.
Okay, and we also have a question sent by Nicolas from Valencia. He said, can you go back and explain with more or less details the chart showing the results from supersymmetry and foremost the R parity violation?
Okay, now you can see the slide. You meant this slide with the supersymmetry results?
You have to share the slides. We're not seeing this right now.
I try to. I cannot share the screen. I don't know why. Oh, okay. Okay. So in this chart, I don't present well, it's not the details of the analysis are not presented, but you can find it in all of the papers related to each one of them. You can see each analysis is associated with one of the paper. In the RPV violation, you have the different values of exclusion for the different supersymmetric particles. But each one of the analyses have their own details for them. I cannot give you a detailed information of each one of the analyses right now. The section of the RV is in the lower part.
Okay, we have also a question sent by Felix, also from Valencia. He said, what do you mean with the pseudo experiment?
Yeah, pseudo experiment is you have something that you have the Monte Carlo, and you have a shape of your histogram, for example. You modulate this shape with a fit, then you throw a random with this function that you build. You throw in the program with different random numbers. You throw you ask the program to produce this this function from the fit. So with random numbers, it will give you a small deviation of what you expect. These random numbers can vary depending on, for example, your energy resolution, your muon or electron efficiency. So you give these random numbers of the parameters of the function, you give them some kind of freedom that correspond to something that you see in the experiment. This, you do it many times, thousand, million of times, and you call this pseudo-experiments. So this one, each one of these pseudo-experiments that you throw will give you a point into the distribution that I showed for the spin and parity. And then you get this, you get the distributions. And the same you do it for the signal, or for the model that you want to compare, you do for the both.
Okay. Okay, so I think we have no more questions. That was a nice presentation and discussion. Thanks, Isabel, again for your presentation. We also thank the participants in the Hangout and also all the viewers. We hope to see you in a few weeks for another Latin American webinar on physics.
Okay, thank you very much.
Gracias.